Each one of these uranium fuel pellets releases enough thermal energy to produce 1 million kilowatt hours of electricity.
No, that's already wrong. Now, if you miss this step, you're going to miss the whole fuel cycle. I'm J.R. Majewski. I spent 23 years in the nuclear industry. I received new fuel at commercial reactors. I've managed refueling outages, and I've led the spent fuel program at multiple reactors across the country. Now, there's a ton of these videos on YouTube. They're made by people who are just clipping content together, and they get it wrong. So let me show you what they got right, what they got wrong, but most of all, let me show you how enriched uranium is actually made. Step 1 is the mine. Uranium ore comes out of the ground at concentrations that would surprise most people. We're talking about 0.1 to 2% uranium in most deposits. The highest grade mines in the world are in Saskatchewan, Canada. They run above 20%. And that's exceptional. Most ore is far leaner than that. Now, the ore, it gets crushed, ground down, and mixed with water to form what's called a slurry. And then it's hauled to a mill. Step 2 is the mill. Now, at that mill, the slurry is treated with acid. That acid selectively dissolves the uranium and leaves everything else behind. What comes out of that process is uranium oxide, U3O8. Most people know it as yellow cake. It's a coarse powder, typically yellow to green, and that is all the mill produces. The mill does not convert it to gas. It does not enrich it. It produces yellow cake and stops. Step 3 is the conversion. Yellow cake cannot directly go into a centrifuge. It has to be converted into gas first. At the conversion plant, yellow cake is chemically processed into uranium hexafluoride, UF6. That is the gas that can actually be fed into enrichment centrifuges. In the US, the primary conversion facility has been operated by Honeywell in Metropolis, Illinois. Step 4 is enrichment. You see, natural uranium is 99.3% U-238 and 0.7% U-235. U-235 is the isotope that sustains a fission chain reaction. 0.7% is not enough to run a commercial reactor. You need 3 to 5% for reactor-grade fuel. Weapons-grade fuel requires above 90%. And that gap between 0.7 and 3 to 5 is what enrichment closes. A centrifuge is how it's done today. The UF6 gas is fed into a centrifuge, spinning at extremely high speeds. The U-238 is slightly heavier than the U-235. That causes the heavier molecules to concentrate towards the outer wall. The lighter U-235 concentrates towards the center. Now, that separation is small. One centrifuge pass does almost nothing, so you have to cascade them. Hundreds to thousands of centrifuges in sequence, each pass incrementally, increasing the U-235 concentration. And by the end of the cascade, you have enriched uranium hexafluoride at reactor grade. And today, the U.S. relies heavily on enrichment capacity from European suppliers and has historically purchased enriched uranium from Russia under the megatons to megawatts program. That program converted 500 metric tons of Russian weapons-grade uranium into fuel for American reactors over a period of 20 years, and it ended in 2013. The enrichment dependency it leaves behind is a live national security issue right now. Now let's move to step 5, fuel fabrication. Enriched UF6 leaves the enrichment facility in solid cylinders inside large steel containers. At the fuel fabrication plant, a separate facility, the UF6 is heated back into gas and chemically converted into uranium dioxide powder, known as UO2. That powder is pressed over several tons of hydraulic pressure into small cylindrical pellets. They're roughly a centimeter in diameter and 1.5 centimeters long. These pellets go into a furnace at extreme temperatures for about 24 hours. This sinters the powder into a dense ceramic, hard, stable, and capable of withstanding the heat inside of a reactor core. Now here's where the 2.2 million view video gets its opening claim wrong. It says one pellet produces 1 million kilowatt hours of electricity. The actual figure is about 45,000 kilowatt hours per pellet. One pellet equals roughly 1 ton of coal or 149 gallons of oil. Now back to fabrication. The sintered pellets are loaded into zirconium alloy tubes, Zircaloy. It's hard, corrosion resistant, and transparent to neutrons, meaning neutrons pass through it without being absorbed. That last property is a non-negotiable for fuel rod cladding material. Pellets are stacked end to end inside the tube, and the tube is sealed at both ends. That sealed tube is what's known as a fuel rod, and fuel rods are bundled together into what's known as a fuel assembly. The number of rods per assembly depends entirely on the reactor design. Now in America, a standard pressurized water reactor uses a 17 by 17 rod configuration. That means up to 264 rods per assembly. A boiling water reactor uses a totally different geometry. A can-do reactor, the Canadian heavy water design, uses a 37 rod bundle. Those are not interchangeable because each reactor requires its own specific type of assembly. Now step 6, the reactor itself. Fuel arrives at the plant in a sealed transport container, and at this stage, before irradiation, the fuel is mildly radioactive. The U-235 and U-238 emit low-level alpha and gamma radiation. Workers handle these new fuel assemblies with standard precautions. It's not casual, but it's not the most radiologically intensive work at a facility. That changes completely once the fuel goes into the reactor, because inside the reactor core, fission begins. Each fission event splits the atom and releases energy, plus additional neutrons. Those neutrons strike more U-235 atoms, and that chain reaction sustains itself, and the heat produced by it converts water to steam. Steam drives the turbine, turbines drive the generators. That, folks, makes your electricity. A typical commercial reactor runs 18-month fuel cycles. And at each refueling outage, roughly 1/3 of the core is replaced. Single fuel assembly goes through approximately 3 cycles before it's removed. 3 cycles at 18 months each. That is 4 to 6 years in the reactor. Lastly, we have step 7, which is the spent fuel. When a fuel assembly comes out of the reactor, it is a fundamentally different object than when it went in. The fission process has produced dozens of radioactive byproducts inside of those pellets. The assembly is intensely radioactive, and it generates a lot of heat decay. And it goes directly into the spent fuel pool. And that pool is about 26 feet deep. And the water, well, it shields the radiation and removes the decay heat simultaneously. Spent fuel assemblies, they typically stay in the pool for 5 to 6 years, but often longer because they need to cool. And when they cool sufficiently, they are moved to dry cast storage. These are large steel and concrete containers that provide shielding and passive air cooling. They sit on the plant site or at a designated interim storage facility while the country continues to debate permanent disposal. Now, like I said, I've ran spent nuclear fuel programs, and that program does not end when the fuel leaves the core. It is one of the most carefully regulated and logistically complex operations in the entire fuel cycle. Now, folks, that is how uranium is enriched and actually made. From the mine to the mill, from the conversion plant to the enrichment cascade, from the fuel fabrication facility to the core, from the spent fuel to the dry cask. 4 separate industrial facilities before the fuel even reaches a reactor, each one regulated independently, each one a distinct link in a supply chain that most people have never seen or accurately explained. But now you've seen it. And if you want to understand what happens when that supply chain gets cut and why the loss of domestic enriched capacity is one of the most underreported energy stories in the United States, I've covered it in this video. Watch that next. I'm Jared Majewski, and I hope to see you again.